Welcome all of you for these lectures on river engineering. As we discussed in the last class, hydrodynamics equations like Navier-Stokes equations and Saint-Bennett equations, and we also seen there are the solvers like Hecker's models are available for solving Saint-Bennett equations and continuity equations. But still there are the concepts like specific energy, specific force and the critical flow, that what we can use for river flow analysis. Today I am going to talk these simple techniques which you may have read it in open channel hydraulics. The same concept we can use for river engineering. That's the points what I will highlight today. So, we will going to talk about specific energy, specific force and the critical flow. Those are things also we can use it for solving these complex river flow problems when we have very limited flow geometry data, the hydrodynamics data with certain assumptions. So, today I will highlight it when you use the concept of critical flow, specific energy and specific force. What are the assumptions we do it? Are they assumptions correct for that conditions? That's what a river specialist work on, that whether that assumptions what you are there in specific energy, specific force and critical flow are valid for that cases. So, that's the reasons I am going to teach you specific energy, specific force and the critical flow in the context of river engineering. So, looking that we can look at the books what we have edited is open channel hydraulics with Hanif Chaudhary books along with other books. So, we have added new books which we are talking about the critical flow, specific energy and the specific force. That the concept we are highlighting through from referring some of the context from open channel flow of authored by Hanif Chaudhary. So, looking that let us come back to today what we are going to discuss it with specific energy concept, channel transitions, hydraulic jumps, then we can go up to non-rectangular channel looking for the specific energy. So, that is what we did today. Lecture will cover it and next series of lecture also will cover the critical flow concept. Looking that let me go back to a real conditions of the rivers. When you have a river in the hilly regions, you can have a series of the boulders. So, if you can see this, there are the series of the boulders are there and there are the position of the boulders is the higher than the flow depth. It can happen like that. So, if you look at that, if this is the conditions and if I consider the simple assumption is the steady flow, that means my discharge is constant. So, if I assuming that the flow is a steady flow and considering that the same amount of discharge is happening it, or we are not bothering about discharge variability in a time domain, or that is not as significant for us. So, if that is the conditions, if I just try to draw it hypothetical typical behaviors of what could be the velocity variations, what could be the water depth variations. It could like this, because of this presence of these big boulders you can have a stagnation point, the point where the pressure is equal to 0. You can have a drop of the velocity head, the V1 square by 2 G's. So, that is what the velocity head, and also you can look at that I am just plotting this water depth, this is the bed and plus the B square by 2G is the velocity head is equal to the energy head. So, hydraulic gradient line and energy gradient line. So, if you can look it, there are the hydraulic gradient line and the energy gradient lines, and as these boulders passes through that, again the V1 velocity flow happens, the stagnation point is here. After that the flow again happens with a V1 velocities again increases, and because of the presence of these boulders there are certain energy losses happening. That's what is reflected in the gradient of energy gradient line. The energy gradient line, the slopes are indicate because of presence of these boulders the how much of energy losses happen. That's what we can quantify using Manning's equations. So we can have the presence of the boulders, because of that there is energy dissipations. That's what is highlighted through the energy lines, which typically it's indicating that. If you look at another bigger boulders are here, the formations of hydraulic jumps. As you know it, there are the change of the flow from subcritical to supercriticals. If you look at this energy dissipations, what it happens because of the presence of this smaller boulders presence, that's the energy dissipations happens and that what we can clearly know it from the slope of these energy lines. Slope of this energy line, we can always quantify it, how much of energy dissipated because of these positions of the boulders. When you commit to these locations where the flow changes, it reaches to a critical depth and there is a change from supercritical to subcriticals. The hydraulic jump formations happen. There will be a hydraulic jump formations will happen, there are the vortex formations will happen, the energy dissipation. So because of that there will be the change of the energy losses here. So if you look at a typical sections like this, there are the stagnation point of formations, there are the energy dissipations because of bed roughness, and there is a positions if there is a more obstructions there like these boulders, it can have a lot of hydraulic jump formations, and because of the hydraulic jump formations you can have a large drop with the energy because of these hydraulic jump formations. That's what is happens in open channel flow. It also happens in the rivers. If as you look at the typical river cross sections, you can see like this, there is energy losses happening. Now the point is coming it, how we have to quantify it, how to know it, there are the change where the hydraulic jumps is going to happen, what type of energy dissipations are going to happen. Those the things we can analyze for a conditions of steady flow. That means we are assuming it, if it's a flow is a steady flow, and this assumption is quite valid when you talk about, look at that when you have a high flow condition or design flow conditions, what could be the extreme conditions in terms of energy dissipation, in terms of velocity variation, in terms of the flow depth variations. That's what we try to know it from that. That's the reasons many of the steady flow analysis also enough for us to solve these problems. So that's what we do, a steady flow analysis in terms of specific energy, specific force and critical depth analysis. That's what in these figures were very clear cut showing it, how the hydrodynamics varies in a channel, in a rivers with having a different type of big boulders, smaller boulders. There could be a hydraulic jump formation, there will be a stagnation point, there could be energy losses because of bed roughness. All you can understand it if you sketch this figure, how hydraulic gradient line, energy gradient lines varies it. That's and how we can use the concept of specific energy and specific force for this. Let's go for the next slide. Next slides what I am talking about, like we discuss about two basic principles, mass conservations and the linear momentum equations. If you look at these two equations, beyond that we have a energy equations. So we can apply this energy conservation equations in a control volumes. So if you can consider a control volumes, you can apply the energy equations. As you know it, you have the three type of the energy: potential energy, kinetic energy and the energy due to the pressure difference, that is pressure force pressure energy per unit weight. So that's the reasons, if you know it very basic fluid mechanics, that we use the Bernoulli's equations. It's the same versions we can use for the open channel flow, where the total energy per unit weight, we can define as a potential energy. This is the energy due to the pressure per unit weight. This is the energy per unit weight as a kinetic energy. So this is the sum of the three energy. As you know, it is a part of Bernoulli's equations. The same total energy available at that particular cross section, particular sections, we can divide into three energy components. That means if I have any channels, so I can have this hydraulic gradient line, and I can find out the energy gradient line, and the H from certain datum, and this is a Z, this is a H, and this is a V square by 2G. So you can easily have these three components. This from this datum, this potential energy per unit weight, that's what is Z values. This is because of the pressure difference. What will get it, the pressure difference, that energy part, the pressure, the energy per unit mass because of the pressure, and this is the kinetic energy per unit mass. That's what is V square by 2G. Many of the times also you use a alpha part as a kinetic energy correction factors. In that times we consider the flow is not uniform. Flow is not uniform. In the case of the flow is not uniform, we adopt the alpha value, which consider the flow velocity variations in terms of computing kinetic energy per unit weight. So this is a very simple concept, as if you from the fluid mechanics. That's what is idea we have brought it, that total energy or total energy per unit weight, which is called a total head, that's what will have a three compositions: potential energy, the flow energy, or it's called the energy due to the pressures per unit mass weight. Same way you know the kinetic energy per unit weight. So these things we can easily get it for a particular smaller control volumes as a reach. We can consider it, and we can compute these three energy component, which represents our total energy. So connecting the total energy point is called energy gradient lines. So how the energy variability is going it, that's what we look at. So what do we do it? We make it a bit smaller, easier for us, that with a certain assumptions is that we consider it. The first simple assumptions where we put it, that if I consider is the surface as is a horizontal surface. So if I consider the surface is horizontals and the flow is coming, okay, this surface horizontal is my datum. If I consider it, so Z is equal to 0. Z is 0. River bed, if I consider as a datum, then Z becomes 0. So I have this only these two components. Okay. The energy components will have a two components. Now this flow energy due to the pressure difference, and there will be the kinetic energy. That's what is because of the flow is there. Okay, that's the. So if you have these two energy concept, and if you consider is a pressure distribution is hydrostatic, that means you are considering the pressure distributions as close to the flow at the rest. So hydrostatic pressure distributions. The pressure distribution is hydrostatics. So okay, it only varies with the depth. Its pressure distribution a linear triangles, and it's a varies with the depth. As you increase the depth, you will have a pressure density increases. It is a linear functions as discussed any of the fluid mechanics. So, if you have a hydrostatic pressure distributions and if I assume it the channel bottoms as a datums, these energy equations is very simplified it as this form. Okay, it is very simplified. Now, the energy, that means what I am looking at, we are just getting the energy per unit weight for a channels where the pressure distributions is hydrostatic and channel bottom if I consider is as a datum for me. Okay. Then that energy we call a specific energy. So, it is a simplified versions with these assumptions. So, we have a energy, specific energy E is a function of flow depth, the y, v is the velocity, v square by 2g. So, if you look at it, it is very simple functions what we got it as a energy calculations. So, many of the times we use this specific energy instead of these equations, because these two assumptions we can validate it for many of the cases. This assumption can be considered for many analysis to know it how the energy dissipation is happening it. So, that is the reasons we compute the specific energy. That is the assumption you try to understand it, and that is what is specific energy is a energy, total energy per unit weight where the channel bottom is considered is datums and pressure distribution is hydrostatic. That is the specific energy. That is not a, it is a total energy in a open channel flow, in a river flow. So, considering that, now if you look at these equations, it is a very simple way. Many of the time we can consider the river as a rectangular channels. It has assumptions now. Okay. If I consider it, river is a simple rectangular channel, so having a b width and y is the depth of flow. Y is depth of the flow. I can consider it channel is a rectangular channels. These are assumptions. Okay, it also quite valid. If it that the conditions, now these equations again we can simplify it. That if we have the q amount of discharge passing through the steady discharge over this, I can compute it the smaller q, which is the discharge per unit width. That means q by b. Okay, discharge per unit width, smaller q. If I put it that, then I have the y is a variables. So, I can easily write is velocity is q by u, y, q by y. That is very simple things. Discharge is equal to velocity into area. Here we have considered discharge per unit width divided by the depth, it is what will be the velocity. So, that way if I can substitute it, I am getting these equations. Again with some assumptions with having the writing the specific discharge equation in terms of discharge per unit width. If I consider that, my equations comes like this. So, in these equations if you look at that, I have 3 variable and q. Okay. So, I have specific energy, the flow depth, I have the discharge per unit width. So, 3 variables I have, it is established with these 3 equations. Now, I am not going to detail minutely look at these equations and the derivations which we can follow from Hanif Chaudhary books, but let me have a very conceptually understanding that we have the specific energy y and the q, 3 variables, a relationship of specific energy relationship we got it. If we got this relationship, now we are looking at if I make E is a constant, we try to know it what could be the relationship between the y and q. Again I am to repeat it. if I consider E is a constant, that means I am considering a reach of the river where energy dissipations are not happening that order. So, that means energy remains constant at that reach of the river. If that is the conditions, what is the relationship between the y and small q? We can establish it using these equations. This is a very simple thing. Same if you try to understand it, if q is a constant, that means what we are doing, that the river width is not changing it. Whatever the capital Q discharge is coming it per unit width if it does not change it, then smaller q, the discharge per unit width does not change it. So, you can have another conditions, that one conditions one, that E constants, we look at what could be the relationship between y and the small q. That means this is the cases where energy does not dissipate that much. So, we can consider a reach, we can assume it that energy dissipation is not that significant order. We can find out a relationship between y and q. Same way, if I can assume it, the q does not vary it, that means my q amount of capital Q discharge, what is coming, it is a constant, it is a steady flow, and my width of the river is not changing it. Okay. I am considering a rectangular river and the width of the river, it does not change it. If that is the conditions, q also does not change it. In that case, I am looking at what could be the relationship between versus E versus y. So, that is the concept, okay, and more the other derivations and all the things are the basic things, but try to understand it. There can be the two conditions you can have, that one is the E constant, energy dissipation is not that significant order. Second is that discharge per unit width is a constant and not varying that significant order. If that is the conditions, what is the relationship between q and y, or in case of a q constant, what is the relationship between E and y, because the flow behaviors happens like that. So, with this relationship we can understand the different type of the flow. So, if you look at that, the first point what we have done it, that we assume it this q is a constant, there is a smaller mistakes here. So, if you have consider the q is a constant, see if you can write it, the equations becomes like this, simple way. So, we can rewrite these equations when the q is a constant, you can write it like this forms. So, we can get this is a quadratic equations. So, we can cubic equations and you can get the solutions of the y. So, that means if is a q is a constant, we can get a solutions of y E for this, and or we can develop the solution curve for these cubic equations, which are very mathematically, if you look it is a cubic equations where we can get the behavior of the curves. That is what is specific energy curve, which discuss more in open channel flow. That is what is called specific energy curve. That is what give a establishing between. Now, if you try to understand it as q is constant, q is constant. So, discharge per unit width does not vary significantly. So, if you consider that, then there is a relationship between E and Y, that is what we have got. It is a cubical, and nowadays you can solve these equations, it is not a big issue, but let us see what is the behavior of these equations, the solutions behaviors, that if I plot E versus Y, okay, E is the specific energy, Y is the depth. So, that is what is called specific energy curve, specific energy curve. The equation of E y will follow this curve, okay. So, follow this curve, and third one will be a negative values which will come here. So, there is three solutions y1, y2 and y3. For this q equal to constants, you will have a one will be negative, which we should not consider it. It is not physically possible to have a river flow depth is negative. So, we cannot consider that part. So there are the two depths y1 and y2, which is called alternative depth. That means what? We try to understand it from the specific energy curve. For a constant q, you will have the specific energy variations with respect to y is very like this. Okay. So in these points, if you look at from this specific energy curve, very interestingly, there will be a point that will be E equal to minimum. Beyond that, the flow is not possible. Okay. That means for a particular q value, we will have the E minimum, the minimum specific energy. Beyond that, flow is not possible. That minimum specific energy, if a flow is happening it, and that corresponding depth is called critical depth. That is the corresponding depth is called, flow depth is called critical depth. That means a critical depth where at that particular discharge per unit width, the critical depth occurs the point where specific energy is minimum. That is the critical. Beyond that, this flow is not possible. The flow cannot possible for this q value beyond this E minimum value. So we cannot have that. The flow cannot possible. It can go to the E minimum value of this. This is what we call the critical flow. So we divide the flow into two regions, subcritical and supercritical. So the supercritical is this part, supercritical, and this part will be the subcritical. If you look at these behaviors, what did actually happen between the subcritical and supercriticals? No doubt you know it that we can compute the flow Proud numbers in fluid mechanics or open channel flow to know it whether the flow is subcritical or the supercritical based on the flow Proud numbers. As flow Proud numbers lesser than 1, that is what will be the subcritical flow, and flow Proud numbers greater than 1 will give a supercritical flow. That's you, by definition you know it. Let us understand the physically what it actually happens. In subcritical flow, if you look at the flow depth is more, velocity head is less. In supercritical flow, flow depth or the pressure energy is less, but kinetic energy is more. Just try to understand it. I know it, you all know about flow Proud numbers and you know it by definition what will be subcritical, supercritical, but try to understand it, that if that flow is happening it has a two energies now, as we have discussed it earlier, that specific energy representing the two energy. One is the energy, the pressure energy per unit weight, another one is the kinetic energy per unit weight. So if you look at these two energy in a subcritical and supercritical, what are the difference? The difference is that in case of subcriticals, the pressure energy is quite significant as compared to your kinetic energy. But when you go for supercritical flow, the velocity kinetic energy is much more high as compared to the pressure energy. That is the reasons V square by 2G is a higher value. If you look at this graphically, it is a higher value. Here the pressure energy, the kinetic energy lesser. That's way try to understand it. It's not like flow Proud number is lesser than and the greater than 1 to define it as subcritical, supercritical flow, but try to analyze in terms of energy available to the flow, pressure energy and the kinetic energy. So the pressure energy, what we found it is quite significant high in case of subcritical flow as compared to the supercritical flow. In supercritical flow, the kinetic energy is a more dominant as compared to the pressure energy. That's what the point we should try to understand instead of to just remember it, the flow Proud number is lesser than 1 or greater than 1. So that's the point what I want to highlight you. So whenever you get a problem, try to understand it, what are the energy components we are using it, and how this energies varies with respect to the flow depth is a specific energy curve. Very interestingly indicate us there is a minimum points which is the minimum specific energy happens it. Beyond that flow is not possible. That is the point is called the critical flow, and that is the flow depth is represents the critical depth. Beyond that we have two divisions, we have divided subcritical and supercritical regions, and if you look it in terms of flow Proud numbers, we can also find out flow Proud numbers greater than 1 is supercritical, lesser than 1 subcritical, and flow Proud number is equal to 1 at the point of the critical depth. So, that is the concept, we should understand it. Let us understand the specific energy concept in a river point of view. Let me I consider the river width variations are happening it. The same discharge of Q is coming it with variations there. Because of that, as the width is increases, the Q will decreases, smaller Q. The discharge per unit width will be decreasing it. So, if that is the conditions, and that means if I have the conditions, the discharge which is varying it from Q1 to Q2. Okay. So, that means Q2 is higher than Q and Q is that. So, this is the order of increasing. If that is there, and if you draw the specific energy curve, that is the same equations. If you consider the different Q value, the Q2 will follow like this curve, Q will follow this curve, and Q1 will follow this curve. The relationship in E and Y space. Okay. In a Y space, we can find out how the solutions of these values. Okay. That is what is showing it. The possibility of the flow can happen at different E and Y for this constant Q values. That is what we have drawn it, Q2, Q and Q1. Now, let me analyze this curve. Very interesting fact is showing in this curve. As I say that these points are reaching point of this critical flow. The point where we have minimum specific energy is minimum. That the point is shifting it. So, that means as the Q is increases, that we need to have a higher minimum specific energy minimum to maintain that flow. But if the Q is a lesser, you can have a minimum specific energy minimum is a lesser as compared to these ones. So, that way we can understand it that as the river width increases or the decreases, how these minimum energy concept also changes, the critical flow depth also changes it. The critical flow depth also changes it, and the minimum energy concept is changing it. So, if it is a very simple way to trying out the two energy partitioning between E and Y in a with a different value of the Q, and how the regions of subcritical and supercriticals, that is the subcritical, and this is what the supercritical regions with a different Q value. We can plot it and we can analyze it, how the flow can happen it if I have the variations of the Q as the Q variations shown in these graphs. So, try to understand these things for river analysis. Now, if you commit to that river having a bed slopes, it is not the flat. Okay. So, in that case, that means if river is having this a theta angle of the slope, that is the real conditions. The river can have a very gentle slope or the mild slope, like a Brahmaputra river, the slope is in Assam valleys is about 1 by 10,000s, okay, 1 by 8,000s slope, okay, that is very gentle slope. But if you go to the Himalayas, the slope could be a order of 1 by 20. The slope variability will be there. So, the slope is decreasing trend as you go from hilly to the floodplain areas. So, looking that things, if I consider it, there is a slope in the channels in the river and apply the same specific energy concept for Q. Now, we are writing in terms of Q. So, because of that the V equal to Q by A, and also we are considering the alpha, which is the kinetic energy correction factors. So, we have now used the concept of the velocity distributions, which is, as we discussed, will be the logarithmic velocity distributions in a open channel flow. For that we can compute what could be the kinetic energy correction factors. So, that is the reasons we have introduced the alpha value here. Considering the velocity distributions, we can find out what is the kinetic energy correction factors, the kinetic energy per unit weight, that is what we will get it. But being a slope here, we can result the depth, the flow depth here and the vertical distance in terms of d cos theta, and in terms of y we can get it y cos square theta into this part. This is a very simple way, just we have used the a inclined channel or inclined rivers having a theta angles. Okay, that is what we can assume it. The slope of the river does not change that significantly. So, we can assume it that it is having angle theta, and as it is having angle theta, what could be the specific energy equations if I consider the velocity variations in terms of alpha and the Q by A is the Q is the discharge, area is the flow area, and we can write the specific energy more detailed form of a real for a river conditions where it is having angle theta, velocity distributions are there, as well as we consider it the y in terms of the normal depth, the projections part. So, simple geometry, if you look at that, we will get it the specific energy y cos square theta alpha q square by 2 g a square, nothing else. It is a equation energy, specific energy equations for a channels with having angle theta and also considering velocity distributions in terms of alpha. The alpha is kinetic energy correction factors. So, that is what we can write it to get it this formula. Now, let us come to a real problem is channel transitions. Many of the time, as I say, that width of the river can increase and decrease it. Same way in the river we can have a rise and the fall. Because of presence of the boulders, you can have an increase of bed levels or there could be a natural fall. So, there could be a rise and fall, expansion and contractions. The river width can increases and decreases. Because of that, let us use, that is what is called channel transitions. That means it the cross section of a channel changes it such as with channel width, channel bottom slope. You can have a width of the river can change it or channel bottom slope can change it, and there could be a rise or there could be fall, and that is what it transitions. And most of the times these energy losses due to the frictions at these transitions locations can be considered to negligibles. It is not that significant order. Also many experiment is conducted it that it is not that significant order because of if you have a gradually transitions happens it. That is what it is, we can consider it. If you have a that is the consideration, let me try to understand it. There is a rise, okay. This rise, the increasing the bed level, maybe you consider the boulder presence or be maybe a small weir constructions by the engineers. So, if you have a that the conditions, then what will be the flow behaviors? That is let us understand it. So, if that is the flow conditions, there is a flow is coming it which is having the flow depth y1, specific energy as we can consider a channel is horizontals, you can find out the specific energy and the total energy is the same H1 equal to the E1, and you have a y is a flow depth and delta Z is the rise depth, okay, edge equivalent rise. If I consider it, now the point is coming it, if I draw this, that means what will be the specific energy at the section 1 and sections 2. If I compare it, and if channel width is a constant, discharge is Q is the same for us, that means Q is a constant for us, and we are drawing the specific energy curve for that. Specific energy curve for that. We are considering specific energy curve. If you look at that, for the Q is a constant, Q is constant, we can draw specific energy curve. That means if section 1 is here, then what it actually we are computing it. If you look at very simple things, if you look at that, as we have considered, there is no energy losses. So, energy gradient lines can be like this. So, H1 is equal to H2. Okay. So, but the specific energy at this E2, because of energy gradient is flat is here. So, specific energy will be the at the two locations will be E1 minus delta Z. The delta Z is a rise, the specific energy will drop will be there, that is what will be the E2 equal to E minus delta Z. Very simple thing, because of increasing the level. So, the specific energy is going to reduce it here as E1 minus delta Z. If that is the conditions, that means in a specific energy diagrams, one point is lies here, the two will be lies, the two solutions will be lies, either 2 point here or 2 dash here. Is it correct? So, that means the E1 is energy at the upstream point, E2 is energy at the rise point, and that could we have a two solutions, one is 2 is here, 2 dash is here. So, if you look at that way, whether one will, the solution is 2 or 2 dash, that what we have to try to understand here, that as the flow is subcriticals. So, one is lies here, the flow is subcriticals. The 2 is a possible solutions for us, because the flow will be try to remain on the same regime, the subcritical regimes. As we discussed earlier, that when the flow is changes from supercritical to subcritical, there will be some sort of energy dissipations will happen it, or it will go through the critical flow depths. It cannot happen it suddenly at points where the flow will be transit from the flow will change from the subcritical to supercritical. So, if you look at this curve, if the flow is at the one point, the flow is subcritical, then the solution is 2. If the flow is supercritical, the solutions could be 2 dash. That is the understanding what we can do it. If there is a rise in the river bed, that is what we can compute the specific energy and draw the specific energy curve and try to understand it, where does it there lies it. From that we can find out what will be the energy at the E2, whether subcritical or supercriticals. In case of the subcritical, the solution will be the 2 point. In case of supercriticals, the solution will be the 2 dash. So, that is the point, the channel bottom. Now, if you try to understand it, if I try to increase the channel bottom, the delta Z, I am going to increase it, okay, because of any obstruction and anything that if I try to increase the channel bottoms, I have control over that increasing the channel bottom. The flow is really possible, still it reaches the critical depth. That means, the delta Z is the flow at this point, the delta Z I can increase it, and that what I can increasing up to the point where the critical depth will occur, the critical flow rate. Beyond that, flow will not be possible. So, that is what it happens it, the bottom can rise until E equal to critical E value, and that will be the our bits. And if that is not conditions, then what it happens, it will discuss in the next class. So the basically if you look it, try to understand it, that if I have a rise, we can draw the specific energy curve, you can compute E1 and E2, and you try to find out whether the flow what is coming from upstreams, is it subcritical or the supercriticals. So looking that we can always make it very interestingly this figure is indicating for us. So if I have this subcriticals, the flow conditions will be look these conditions, that when the flow is supercriticals at the upstreams levels, that's like the point is 1 is here. In that case the solutions will be the 2 here, that is what 2 points, the flow depth is going to increase it, okay. Flow depth is going to increase it, and you can find out that is what is this curve, you can see that the flow depth increasing is there and the velocity is decreasing pattern is there as the rise is happening, it as the flow is supercriticals. So basically let me I summarize that if the step rise in the channel bottoms, okay, and the channel flow depth decreases the downstream of this step, if the flow upstream is transition is subcritical. So if the flow upstream is a subcritical regions, then the flow depth decreases in the downstreams, the reverse is happens, it is a flow is a supercriticals, the flow depth is increases. Other way around you can talk about also the velocity increase or decrease patterns. As you know it from these diagrams, it has a flow depth, also the velocity. So specific energy is having the flow depth and the velocity head. So if you try to understand it, because of the flow changes from subcritical to supercriticals, the in case of the subcritical flow, the rise of bed, it has effect different as compared to the supercritical flow, where the same rise can have a different effect in terms of flow depth increase or the velocity increase. That all the interpretations you can do it with this specific energy curve analysis. That's similar way we can do it if there is a drop. That's what we can conduct it. With this, let us conclude this lecture.